All right. Hello, my name is Lev Stambler. I'm a PhD student at the University of Maryland under Matthew Quadron, and I also work with the company NeverLocal, which does quantum cryptography, and they try to do quantum cryptography for more existing quantum networks. And today I'll be presenting this paper on information theoretic one-time programs from locally geometric quantum MC0 adversaries. And really the high-level idea is that we're going to construct this cryptographic primitive, which we'll explain shortly, called one-time programs. And we're going to show that we can construct it information theoretically if we have a bound on our adversary. So there's been similar work before, but it's had different conditions, more computational, meaning that there's computational assumptions, and there are additional assumptions on the time that you can keep states coherent. And we'll get into that shortly, but really the big difference with this work is that it's information theoretic and that there's no bound on coherency time. So you can assume that your qubits can stay around for as long as you want. You have as much storage as you want, and you don't have to assume like special hardware devices that some other work has to. So quick outline, we're gonna first go over the end goal, what are we building towards, one-time programs, why they're cool and why they're interesting. Then we're gonna go over some of the technical steps that we need to build our construction, starting with random access codes, a very cool subsection of quantum information theory. Then we're going to talk about how we specifically model the adversary, which turns out not to be like super trivial, but it's not too bad. Start the proof, introduce collision information theory, a type of measure of information used in cryptography. Finally, finish the proof and go to the conclusion. Before that, if there's ever any questions, just feel free to ask the question. And with that, let's get going. Okay, so first, our end goal. So one-time programs are these really mystical primitives. They're really weird primitives because what you're supposed to do is be able to provide Bob a program. And this program should be able to self-destruct after one evaluation. And in some sense, it's not very physical when you think about it, especially in the classical setting. Like I can't send someone an email and have that email self-destruct upon first reading. And it's proven to be impossible both classically and in the quantum standard model. Let's see. So what we're going to do in this talk specifically, though, is we're going to actually show that you can construct a one-time program without any cryptographic assumptions, except for a bound on the quantum adversary. So we're going to model exactly what that means later. And we're going to assume that Alice, the sender, is going to give Bob some noisy qubits. And we're going to use that to show that you can create a one-time program. Again, we'll define noisy later. And of course, impossible in the standard model. So we're not going to get too much into this, but you can build one-time programs from these things called one-time memories, which are a special case of one-time programs, and they're much simpler to think about. And what they are is they allow Alice to give Bob some special box, and Bob can read one message, M0 or M1, but not both. And the other message will self-destruct after reading the first message. Okay, so that's the very quick introduction to one-time programs. There's nothing, without getting too much into definitions, there's nothing else really too much to them from a just defining them point of view and like explaining them. Okay. So we're now going to explain quantum random access codes, often abbreviated QRACs, and they were introduced by Mbinus et al. About 25 years ago. And they're like a form of quantum advantage or something that you can do in the quantum setting that you can't do in the classical setting, where we can encode a string of a set of classical messages into a code bit with n qubits. And with some probability, we're going to be able to retrieve one of these messages from the receiver side. So we can think about Alice and Bob again. Alice the sender, Bob the receiver. And Alice has m messages. And Alice is going to encode each of these m messages into an n qubit state. So somehow all the m messages impact the choice of the n qubit state, and n is less than m. And then Bob is going to receive this quantum state and choose an index of which message Bob wants to recover, applying some special unitary UI corresponding to the ith message. He'll be able to read out the ith message with some probability of success. not 100% probability of success, but some probability of success. Okay, so for the purposes of this talk, we're going to really focus on just the original quantum random access code introduced by Vinacell. And it's a 2-to-1 code, meaning you can encode two bits of classical information into one qubit. And the probability of Bob reading out his bit successfully is 85%. And we're going to use this like cal-e notation to denote the encoding. And really, the encoding we can visualize on this like unit circle representation where we have up here ket1. So it's like the z basis and then this like the x basis, where 1, 0 and 1, 1 are close to 1. So somehow this first bit is close in projected distance to measuring a 1 in the z basis, and then 1 in the second position is close to minus or close in the x basis, and so on. So more visually, let's say we want to measure out the first bit. We're going to measure in the z basis represented by the bold lines here. And then the measurements of projection onto the z basis. And then we're going to be able to guess 1 with 85% chance if the state is 1 in the first bit, and 0 with 85% chance if the state is in the second bit. So the key idea that led to this work is, what if you combine random access codes with error correction? So as we have from above, we have an 85% chance of measuring out the correct bit. So if we take a bunch of different quantum random access codes and encode them in a set of messages, maybe we can use error correction to pseudo-deterministically, so with probability arbitrarily close to 1, recover our original message. And again, we'll show in a second that this is actually kind of a useless idea when you have arbitrary quantum computation. You can't do anything too interesting due to Halevo bounds, but we'll get there in a second. So recall our notation for random access codes. So what we're going to do is we're going to take n states for n length code word. We're going to apply our unitary to encode them into a random access code and then give them to Bob. And Bob's going to choose to decode their code word and recover the original message. So again, we're going to have something like m different code words, and Bob can recover one of the m code words by decoding what Bob reads. So any questions with this kind of setup? So for the remainder of the talk, we're going to take m equals 2 as before. So 2-to-1 random access codes and only 2 code words that we're going to be thinking about. And this slide is kind of showing why this idea of taking 2 code words, encoding them in a classical error correcting code, and sending them over as random access codes isn't the most interesting thing, in that we might as well just send over C0 and C1 not error corrected, send over the original bits of information to Bob, because if Bob has perfect quantum computing, Bob can recover C0 and C1 anyways, because what Bob can do is Bob can apply the decoding unitary in superposition, read out C0, undo said decoding, and then read out the other bit. And the reason for this is because if you can decode with some arbitrarily close to 1 probability of success, you can do a weak measurement and barely affect the state and read out both bits of information. And it's also a very similar reason for why one-time memories can't be done in the standard quantum setting, because if you can read out one of the messages with arbitrarily close probability to 1, then you can do this kind of weak measurement thing and recover the other message. Yeah, so this idea above can also be used to bound the probability of success for random access codes, and it connects to information theory, and there's a whole bunch of work there, but I think it's interesting to mention, but not too important to this talk. So let's see. So I guess the question of this talk, and really what this work asks, is what if a weak adversary cannot decode in superposition? Because presumably superposition decoding is not like a very simple circuit. It has some amount of depth. And if that circuit cannot be done on a quantum state by the adversary, then maybe we can actually get something like one-time programs, where the adversary can only read out C0 or C1. So that's the key question of this paper. So the idea for the construction is if the quantum adversary can only do these noisy decoding on these states psi1 through psi-n, then presumably if they try to decode in superposition, they're going to mess up their quantum states too much. And the hope is that instead, they can only recover one. So Alice is going to send these two set of states, so psi1 through psi-n. And if Bob wants to recover C0, he's going to have to measure in C0 and the Z basis. And if Bob wants to recover C1, he'll have to apply a Hadamard and measure in the X basis or in the Z basis after that Hadamard to recover C1. And notice that in both cases, the depth of the quantum circuit is at most 1 or 2, if you include measurement as counting for the depth. And the decoding is entirely classical. And I just want to point out here that our construction uses random linear codes to encode C0 and C1. So the construction does run in classical exponential time, something we hope to improve upon in further works, but the use of random linear codes is part of the proof. And we'll see why that is the case later, or it helps with the proof.
So sorry, can I interrupt and ask a quick question about the notation? So C0, the whatever index I. So index I is denoting what? C0 is, I guess, the the code word for the 0th message, and I is the index of the code word, like the ith letter in the code.
Yeah. So we're working over binary alphabet, so it's like the ith bit. Yeah.
Right. So it's a string, and then okay, you're sending. I see.
Yeah.
Okay.
Yeah.
And then
so
if the message. Sorry, just a quick follow up. So so here the message is only 2 bits, but the code word, I guess, is going to be n bits. At least that's the way you're doing it. Okay.
Yeah. So
I see. And of course, originally the. Sorry, go ahead.
Oh no. Yeah. So we're sending n quantum random access code states. So each one of these states is a single qubit, and each one of these states encode this pair. Like, so this state encodes C01, C11. So it encodes the first bit of C0 and the first bit of C1.
Right. Right. No, I was just saying that initially the whole point of random access codes was, I guess, that you can use fewer qubits to send more classical messages, but now we're sending many quantum messages to send just 2 classical messages, but we are trying to get some additional property out of it.
Yes.
Which
Okay. Yes. So maybe to linger here a bit more, we're sending 2 classical messages, but these 2 classical messages aren't necessarily 1 bit. They're going to have, say, like k bits of information in each message. And the property of the random access code that we're using is this ability to, with probability better than half, so like 86%, recover the first bit or the second bit with a very simple circuit. It's just either like right as above, as you see here. To recover the first bit, we just measure in the Z basis, and to recover the second bit, we just apply Hadamard first. And we're going to use these 2 properties together to be able to, like, with probability close to 1, decode and recover C0, or decode and recover C1. And like the work of this paper is really just showing that decoding in superposition you cannot do in a low depth circuit.
Decoding in superposition you can't. That's okay.
Yeah, or non-adaptive.
And this. Right, and the superposition part is important because then you can assert potentially that you could have recovered both using the weak measurement thing. Is that why?
Yeah.
Okay.
Yeah. So if you are able to decode in superposition, you can recover both C0 and C1, and you no longer have a one-time memory. But using this idea, so that's the.
Got it. Thank you.
Thank you. Okay. So some more questions. I guess I'll move on to how we define the adversary.
Sorry, the EIs are like these are errors, or what are E1,
yeah.
E2, En?
Yeah, so the E's are errors here. So they're like implicit errors from the measurements. They're not actually added by Alice. It's more that when you measure, you can't recover C0, 1, for example, with 100% probability. So we're going to just think about the measurement error as E1.
Got it. Thank you.
All right. So I guess if there's some questions, we're going to get to how we constrain the adversary, which we call Bob. For this talk, we're going to assume that Bob is given as an auxiliary set of qubits and qubits from Alice in a d-dimensional grid. And this d-dimensional grid is more or less without loss of generality. There's different ways to arrange qubits, but for simplicity, we're just going to assume a d-dimensional grid. It does not have to be 3-dimensional, but it does have to be a constant. So that's where this like G, Q, and C uppercase D comes from. We have a geometrically constrained adversary, and this has been considered in many different works, looking at can you get quantum advantage from geometrically constrained circuits. And this lowercase d is a depth bound. So what depth of circuit can be applied? And we're going to assume that all gates are local. So they're, in this case, in this graphic, only on 2 qubits at a time. So all these things are constant. And we can see this illustrated for the case where we have a 2-dimensional grid, and each layer in this graphic represents one step in time of the circuit, and all the yellow squares represent the unitary being done. So this is what we're going to assume that Bob can do on the states that Bob is given by Alice. So I think it's a pretty simple model. It's used in multiple places. Unfortunately, this model is kind of it's not adaptive. Bob can't like stop his computation midway, his quantum computation midway, and adjust the circuit. That is being left to follow work. But so further, we're going to assume that because we're not, besides the bound on quantum computation, we're not assuming that there's any sort of computational bound. So we can model Bob as being an exponential time classical computer with Oracle access to a single application of geometric QNC circuit. And the reason for this is because we're trying to model auxiliary states given by Alice. And it's like this neat trick where, because we want to make sure that Bob can only do one circuit of a limited depth on the input state, but we also want to allow Bob to do any other classical and quantum computation unrelated to the input state, the exponential time for Bob also allows Bob to actually simulate quantum computation, which is, I think, pretty neat. But really, the state that we have here is Bob is given classical auxiliary messages as well as their set of qubits rho. And then Bob can write some classical computation to decide what G, Q, and C0 circuit to apply to their input auxiliary circuit, input qubits. Bob will then measure the qubits and then do more classical computation. So this is the model of the adversary. If there's any questions of this, please let me know. This is important for the remainder of the talk. Okay, so the features of this model is that Bob can only apply one circuit, but at the same time, as I said earlier, Bob can simulate any quantum circuit of any polynomial depth. And you check really in the paper, we just use C instead of exponential. So like any classical computation, not too bounded to be exponential, because Bob can even run like super exponentially, and the constructions just still work. But really, the use of this very strong classical adversary allows Bob to simulate any external quantum computation. So even like, and the reason that this is important is because we can imagine a world in 20 years where we do have real quantum computers that are fully fault tolerant, but we still have these quantum networks that we can send qubits, and we can't send, unless we encode the qubits fault tolerantly over the quantum network, then the receiver still cannot do unlimited computation on the received qubits. That's like the hope for what we're trying to model here. Yeah. Okay, so now to introduce some notation and how we start thinking about things. Whenever we're talking about depth-bounded, constant depth-bounded quantum circuits, light codes become very popular to use. And the idea is we're going to ask what qubits can have some impact on each other when we run a circuit. So if we imagine we have a two-dimensional grid, and each of these black dots is qubits, these yellow highlights right here represent the set of qubits that are somewhat independent of each other. So this yellow box cannot, the qubits in this yellow box, if you apply any circuit of, say, depth to in this two-dimensional grid, cannot affect any qubits in this yellow box, and so on. And we're going to talk about these as cubes, and the yellow region are going to be these inner cubes denoted CUI, and the blue regions are going to be these CU tilde outer cubes. And really, these yellow regions are the ones we're going to focus on throughout the talk, and we're going to kind of discard in the proof the blue regions. But really, as in any kind of geometrically bounded argument, these light cones are important. So now we're going to start explaining how we work up to get a proof. Okay. Yeah. So because we have a non-adaptive circuit, Bob was just applying the circuit once, we can reorganize our measurements to make the proof a little bit easier. And really, the key idea is that we're going to first give all the information in these blue. We're going to give all the information in these blue regions to Bob within the proof. So in reality, Bob does not have access to all those qubits, but yeah, we're just going to assume that Bob learns them. And then Bob is going to perform the computation on the yellow regions, one measurement at a time. And this way, we're going to bound the amount of information that Bob learns about both code words, kind of one inner region at a time, right? So Bob's going to look here, and then look here, look here, and then look here. And we're going to go over this again later in more detail, but that's kind of the key idea. We're going to want to develop some sort of progress bound. So as I said, our goal is to develop this progress bound. And really, at the end, we want to show that the amount of entropy and minimum entropy, for those familiar with cryptography, is sufficiently high in either the code word, the first code word or the second code word after all measurements are done. And for those who have done cryptography before, Shannon entropy is not cryptographic and cannot be used in this scenario. But initially, this paper was attempted with minimum entropy, but minimum entropy is a measure of worst case guessing probability, but it's almost too strong. It loses a lot of resolution, and we don't get a result. So really, that leads us into this next section, where we're going to be talking about collision information theory. This is also called Renyi entropy of order 2, but in certain cryptographic contexts, it's known as collision entropy, here denoted HC. And all we're doing with relative to Shannon entropy is switching the order of the log and expectation. And really, it's a measure of the expectation of a probability of seeing a random variable. So we have all these somewhat dense definitions here, but they're just as what you see with Shannon entropy, just things reversed. And this IC is a measure of mutual information. So how much information does Y reveal about X? And I believe that it's not symmetric as it is with Shannon entropy. So the order matters here, and then IC X, Y given Z is how much information Y reveals about X, conditioned on knowing random variable Z for the adversary. And really, the reason that collision entropy is used in our setting is because you have this nice Markov chain inequality. If we can lower bound the collision entropy on a random variable, then we can upper bound the probability of guessing said random variable. Because we're talking about expectations, and it's a very simple Markov inequality from there. And there's a couple other useful properties that we're going to go use within our work of collision information theory. And one of them is this convexity that we have in classical information theory, where if we have 3 different distributions where P of X is convex in Q and R, then we have this convexity bound that we know from standard information theory. And this can be used to upper bound some values. Okay, so bringing it back to our talk, remember we have this cal-e node encoding our random access codes, and we're going to want to bound some 3 different quantities having to do with collision information theory and random access codes. We're going to want to upper bound how much information any adversary, any Bob, can learn about one of the bits. So that's like I greater than symbol. We're going to want to bound how much information Bob can learn about one of the bits given complete knowledge of the other bit. That's just like I tilde. And then finally, we're going to want to bound the amount of information that Bob can learn about both bits. So this is for any measurement, Bob's going to apply the measurement, and then this is the amount that Bob learns about B0 and B1. Quantities we're going to define over uniformly random and independent B0s and B1s. So B0 and B1 here are going to be drawn from a random distribution, and then these will be constants that we're going to use throughout the talk. And we're going to try to calculate them in 1 second, but before we move on to that, any questions about this setup? I know it's a bit dense with notation.
Sorry, can you remind us what mu was?
Yes. Oh, yes. Mu is any measurement. So we can think about mu as like some P of M, and this is going to be the classical outcome of said P of M, or the classical distribution of outcomes.
Okay, got it.
Yeah. So recall we're working over these QNC circuits, and what's convenient about them is we can really think about just like what the output measurement is, because we don't have any adaptivity within the circuit. So in some sense, it's a very classical quantity where the only quantum part is this mu, being the quantum measurement on your random access code states. So via somewhat brute force, which we're going to explain in a second, we get these 3 quantities that we can upper bound. And what we can notice is that conditioning on giving away the other bits does not actually help us learn that much more about this qubit. So that's pretty nice. And the amount that we can learn in total about both bits is not that high. So each bit contains each B0 and B1 contain 1 bit of information, where the whole state contains 2 bits of information. But really, we have a decent bound on what we can learn. And the way in which we do this is we're going to use the convexity of information, collision information. So again, as a reminder, as we had before, when we have a probability distribution, which can be written as the convex sum of 2 others, we have that the information, the collision information is convex in those probability distributions. And this is nice because for those familiar with like extremal POVMs, extremal POVMs allow us to kind of model extremal POVMs allow us to model the extremal parts of the space of POVMs, and any POVM on say 2 qubits can be written as a convex combination of extremal POVMs. And extremal POVMs are limited in size. So if we have, if we're talking about the space of qubits, that's just 2, we have at most 4 extremal POVMs. So now, using the convexity of the above that we have here, we really only have to ask a question about bounding how much information extremal POVMs can give us relative to these quantities. And because they're limited in size, we only have 4 elements, 4 measurement outcomes. Then we only have to brute force search over a set of 4 possible outcomes. So as we have it here, if any POVM can be written as a convex combination of extremal POVMs, then the information collision entropy can be upper bounded by this convex combination of the information of this collision information from the extremal POVMs. And now we just have to upper bound this right-hand quantity in here. So for example, again, we're going to talk about upper bounding this bit information, and we're just going to have to upper bound this value here, where pi is going to be an extremal POVM, so only 4 elements. So these are 2 by 2. We can think about them as is the connection okay?
Oh, sorry, I was just asking because it could be that it's just my system. I was just checking for others if it's okay, because I'm missing some words in between, making it a bit harder to follow.
Oh, sure. I can also go over. I can go over that again. Is there something specific that you would like me to go back to?
No, it's okay. I mean, I'm trying to follow. It's okay. I just wanted to make sure. Yeah, sorry. Let's
Sure.
let's keep at it. I'll interrupt you if I get completely lost.
Sure.
Sorry. Thanks.
So yes, now we have. So now we're going to be brute force searching over the space of 2 by 2 matrices with the set of 4 2 by 2 matrices. So the set POVMs with 4 non-zero elements. And the approach is going to be some grid search plus pruning. And then we're going to basically iteratively discretize the space. So we have a visual coming up here. Yeah. So the visual explains it a bit better. We're going to start with this like more generic space. And then we're going to upper bound in each of these grids the maximum and minimum possible value of our bit information. And then we're going to throw away the ones that have too low of a minimum value to too low of a maximum value to possibly be the upper bound on this bit mutual information. And then we're going to iteratively refine. When I set out in this project, I thought that the code would be much easier, but turns out it was quite a bit more than I expected. But so it's all written in Rust and up there on GitHub somewhere. But yeah, so we do this somewhat brute force search approach to upper bounding these 3 values. Now that we have all the key pieces of our work, we're going to start combining them to get our final proof. Before that, we're going to introduce just one last bit of cryptographic useful lemmas. And this is what's called the leftover hash lemma. And it's used quite frequently in cryptography. And it says that for any 2 universal hash function, if we take some input that has sufficiently high minimum entropy or collision entropy by this Markov bound property from earlier, and we put it into our 2 universal hash function, so h lowercase h is our 2 universal hash function, then h of s is going to be statistically close to uniform. And this will be important, as we'll see. And we're going to combine this idea of leftover hash lemmas with random linear codes, which we'll explain more in a second. But it's important to note that random linear codes saturate the Shannon bounds, so we can really pack a lot of information into them, which is important for the parameters to work out within the paper, but we're not going to get too much into specific parameters here. Unfortunately, they do the code in exponential time, meaning that our protocol runs in exponential time. But importantly, the generator matrix of a random linear code is a random matrix. And we'll see why that's important in a second. So we're going to just first remember what our protocol does. We're going to have these random access code states and them. We're going to pass n states to Bob. And then Bob can choose to decode in the z basis or the x basis to recover C0 or C1. Now, the key point of the proof is that if we look at, say, some subset of C0, C1, then we can think about it as being some subset of the rows of the generator matrix G multiplied by a random or a high entropy message word. So right in error correcting code, if it's linear, we just encode the error correcting code by multiplying the underlying message by the generator matrix to get our code word. And if you remember these CUs, they're going to be the inner cubes right here. We can think about the information associated with these inner cubes as using this notation. It's a bit abusive notation, but if our size of these inner cubes are sufficiently small and the entropy of the code word that we have is sufficiently large, then this these inner cubes, the information in these inner cubes, are indistinguishable from random because G is some compressing random linear function, so it's a 2 universal hash function, and then the information associated with these cubes are indistinguishable from uniform. This is really the key trick that we use in this paper. So again, if there's enough information, if there's enough entropy left in the code words, then these yellow regions are going to look indistinguishable from random to the adversary Bob if Bob is only looking at one yellow region at a time. So looking at this again, we're going to have a set of auxiliary states. We're going to, in the proof, give those all to Bob. And then after that, we're going to want to show that C0 and C1 have sufficient amount of entropy such that we're going to assume that Bob learns more about C0. So imagine in the end, the amount of information Bob has about C0 is equal to that or more than that of C1. And we're going to show that C1 is going to be indistinguishable from uniform, and then Bob's going to apply his unitary measure. But then we want the bound amount of information that Bob has about C1 after that. And we're going to show that that's still not that much. So C1 still has a high amount of entropy. So then in the next measurement, the next inner cube that we have up here is still in this next inner cube. So if Bob first measures this inner cube, he learns some information about C1. Then Bob will measure this inner cube. And we're going to want to show that that's still indistinguishable from random. And then we're going to continue this process iteratively as a progress bound throughout the whole computation. And if you guys remember, we have this these three constants, this bit accessible mutual information. And they're specifically for IID quantum random access code states. And we'll show we do show in the paper that each of these yellow cubes looks IID for most of the computation to Bob in one way or another. So we can use these three numbers to upper bound how much information Bob learns about both code words. Yeah. So within the parameters, if we use a random message for C0 and C1, that's about 0.4 n for the number of qubits n bits of entropy because random linear codes saturate the Shannon bounds. And if we look at these total numbers, we have about 0.65 bits of total information we can learn from both code words, assuming that everything looks IID. So then 0.4 plus 0.4 is 0.8. And if we wanted to say that Bob recovers C0, then Bob has to take out 0.4 n bits of information. And then because the total amount of entropy is 0.65, then we're going to have some leftover entropy no matter what in the other code word if Bob can recover C0. It's a bit trickier to combine it with combine these ideas with the progress bounds, but this is the core idea. But really, we're saying that in the end, Bob has a lot of entropy left on C1, and this entropy grows linearly with number of qubits. And so the probability of Bob being able to guess C1 after all of his measurements is still exponentially low. And then finally, if we have this probability of Bob guessing this last code word in expectation being exponentially low, we can just use a simple Markov bound to get that the probability of Bob guessing C1 with extremely high probability is exponentially small. And that concludes the key proof ideas. So any questions on the proof ideas? We'll move on. And then finally, the question is how to get stronger notions of security, because here we're encoding random code words. And we have this non-uniform notion of security. And again, we're going to use our leftover hash lemma to get some uniform, to show that the hash of C1 is uniform. And now the hash of C1 is used as the one-time pad in our actual protocol. I wouldn't worry about this too much. It's more of a simpler common technique that can be used. But really the key idea is that our amount of entropy in C1 does scale linearly with the number of qubits. And so the amount of auxiliary information scales sublinearly. I'm not actually sure if it's a log of n. I don't know how that got in there, but it does scale sublinearly. So the amount of auxiliary classical information. So we can we can show that we have enough entropy left over to be a proper one-time pad and encode some other message. So getting to the conclusion of this talk, we introduce one-time memories that are information theoretically secure from error correction and quantum random access codes, and provide some new bounds on collision entropy. But I guess this is a question of, can you remove the adaptive constraint? This is something I'm working on in the progress of actually, I think Atul has a paper. Some other people in the past have like depth-bounded proofs of quantumness. I'm using some ideas from there to show that this type of protocol would be secure against an adaptive adversary. And then also, can we remove random linear codes because they take exponential time to decode? So our protocol runs in exponential time, which makes it effectively useless in the real world. But yeah, and yeah, that's it for my talk. I'll happy to take questions. Yep.
Yeah. So can you go back to the picture where you had the circuit with psi 1, psi 2, psi n, much before? Yeah, one of these. Yeah. So this psi 1, it looks only at C0, 1 and C1, 1. Yes. Yeah. So it looks like it's some sort of a direct, we are doing different coordinates separately. So there is no joint encoding being performed. I mean, one could imagine that you look at the whole of C0 and whole of C1 and construct psi 1 to psi n together. So is that something worth thinking about, or it's not?
Yeah, for sure. Yeah, so there's no joint encoding here. I think it could be interesting to think about what joint encoding would do. But part of the feature of this work is that, like, let's say we want to assume that we have like quantum networks. And we're assuming that Bob cannot do too much computation on his received state on the quantum network. So we would kind of think the same holds for Alice, the sender. Yeah. So it's very simple encoding.
Okay. So Alice needs to do the encoding of each coordinate separately. Yep. Yeah. Okay. Yep. The second question was, you said you use random linear code. But what particular property of the generator matrix can we say that there should be some part of it should be high rank, or every submatrix should be reasonably high rank? Is there a linear algebraic complexity of the generator matrix which would still suffice for your proof?
Yeah, so I think so. It's that we need the submatrices or sufficiently small submatrices to be 2 universal hash functions. I unfortunately lack familiarity with the coding theory to be able to say like you can use some other type of code that's efficiently decodable. I think that would be an interesting question to ask.
Thank you.
Can I ask a dumb question? So this is just about the literature, so maybe it's already very clear. Does the impossibility of one-time programs or one-time memories also apply in the, say, the random oracle model or these kinds of things? Or?
Yeah. Any sort of like, there's variations on it where you're going to ask, okay, we're going to restrict our class of one-time programs. So you can almost think about like, if you guys know like quantum tokens or one-shot signatures as being a sort of one-time program. If you're talking about general one-time programs, then in the random oracle model of virtual black box obfuscation model, any of these things, they're still impossible for always the same reasons that if you can deterministically get the output. Sorry?
Yeah, I was just going to say the same argument you're going to say. Okay.
But they are possible in this model where you assume you have classically accessible oracles. So you have to make classical queries to the oracles. You can't make quantum queries. And in that case, you can build one-time programs. And actually, with Neverlocal, we're working on applications of this. But yeah.
Right. But that doesn't, is it, in your view, a good model or a good assumption to model the real world, that you only have classical access to certain oracles?
I think it depends on the use case, but so trusted execution environments, I think you can more or less model as classically accessible oracles in certain scenarios. So for example, like TEs in the real world have this problem with like ephemeral state where like it's really hard to, they keep getting broken, like these rewinding attacks that keep being broken. So it's like hard to make them one-time programs, but they seem to be okay for like stateless oracles. So that's like the relationship, yeah.